Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we are going to discuss the topic Lorenz Transformation. So, topic is the Lorenz Transformation. We have already discussed Einstein's postulates and their consequences. Now, these Einstein's postulates provide a first step in the resolution of the difficulties we presented in previous lectures, but a more formal mathematical basis is needed to give the theory its full power to calculate the expected outcomes of a wider variety of physical processes. For example, we might wish to compute how the results of measurements of an energy or a magnetic field or electric field strength differ for observers in relative motion. So we require a set of relationships called transformation transformation equations that that relate observations of a single event by two different observers, right? Now, in these transformation equations, an observer S is at rest in one inertial frame. Second, or B, another observer and other observer S prime is at rest in a different inertial frame in a different inertial frame that is in motion at constant velocity with respect to S. with respect to S, and third thing, a single event is observed by both S and S prime, right? Now the event occurs according to each observer at a particular set of coordinates in three-dimensional space and at a particular time, right? Now, knowing the relative velocity, knowing the relative velocity of S and S prime, we wish to calculate the coordinates x prime, y prime, z prime, t prime of an event as observed by S prime from the coordinates x, y, z, t of the same event according to S, right? So these coordinates, to find out from these coordinates, knowing the relative velocity of S and S prime. Now we simplify this problem by always choosing the x and x prime axis to be along the direction of relative velocity as shown in the figure. The situation is like this. We draw a figure. X, Y, Z. There is another frame of reference. This color. This is X prime, Y prime, Z prime, right? This is the S prime observer with its own inertial frame of reference. This is the coordinate system of observer S. As we said, this S prime observer is moving relative to S with velocity u, and the motion is taking place along x-axis, right? So there is some event going here. There is some event, right? We have observer S prime. We have another observer S. This is my observer S. This is my observer S. So both are looking at this event, right? According to this S prime observer, the coordinates of the event are X prime, Y prime, Z prime, and T prime. And according to observer S, the coordinates of the event are X, Y, Z, and T. So this is figure 1. So we want relationship between these two coordinate sets, X prime, Y prime, Z prime, T prime, and X, Y, Z, T, right? So let us move. Now this problem can be solved using the classical kinematics of Galileo and the resulting Galilean transformation equations are x prime is equal to x minus ut, y prime is equal to y, z prime is equal to z, and t prime is equal to t. So let me name this set of equations as 1, right? So these are called Galilean transformation equations. X prime equal x minus ut, y prime is y, z prime equals z, t prime equal t. Now the first of these equations is consistent with our common sense, and the fourth equation t prime equal to t was simply taken for granted in classical physics. Now the relativistic versions of these equations, or I should say the relativistic relationships we seek, have come to be known as the Lorenz Transformation equations. They are named for the Dutch physicist H.A. Lorentz, H.A. Lorentz, who proposed them before Einstein for quite a different reason and who was not fully aware of their implications about the nature of space and time. The Lorentz transformation equations are, let me use another color, x prime is equal to x minus ut over under root 1 minus u square by c square, which is equal to gamma times x minus ut. Y prime is y, z prime is z, t prime is t minus ux by c square over square root of 1 minus u square by c square, which is equal to gamma times t minus ux by c square. These are my, name them as 2. These are my Lorenz transformation equations, right? Let me check them. X prime is equal to x minus ut over under root 1 minus u square by c square, which is gamma times x minus ut. Y prime is y, z prime is z, and t prime is equal to t minus ux by c square over under root 1 minus u square by c square, which is equal to gamma times t minus ux by c square, right? Note that an object located initially at the origin according to S, that is x equal to 0 at t equal to 0, is also initially located at the origin according to S prime, that is x prime is 0 and t prime is 0. So that is, if you put x and t equal to 0, you will get x prime equal to 0 and t prime equal to 0, right? Now in these equations, we have used the Lorentz factor. So in these equations, we have used the Lorentz factor gamma, defined as gamma is equal to 1 over square root of 1 minus u square by c square. We name it third. It's also convenient in relativity equations to introduce the speed parameter. speed parameter beta, defined as the ratio between the relative speed u of the two coordinate systems and the speed of light. That is, beta is equal to u over c. Let me name it 4. Now the range of gamma, is from 1 to infinity. And gamma is 1 at low speed, where u is much less than c, or beta is much less than 1. And gamma is infinite at high speed, where u approaches c, or beta approaches 1. Notice that the Lorenz transformation equations reduced to those of the Galilean transformation equations, that is equations 2 reduced to equations 1, when u is much less than c. And all classical results agree with the experiment. When u is much less than c, only at high speeds must we take relativistic effects into account, right? Now these Lorentz equations, is equation 2, permit us to find space and time coordinates. So let me write it. Equation 2, we have named our Lorentz transformation equations as equations 2. So equations 2 permit us to find the space and time coordinates in S prime if we know those in S. Suppose, however, that we wish to know the coordinates in S given those in S prime, right? From the point of view of S prime, In figure 1, that is this figure, so from the point of view of S prime in figure 1, S appears to move in the negative x or x prime direction. I repeat, in this figure, from the point of view of S prime, S appears to move in the negative x or x direction, x prime direction. So we can obtain the inverse Lorentz transformation by merely switching primed and unprimed coordinates in equation 2, that is Lorentz transformation equations, and substitute minus u for u. So to get inverse transformation equations in these equations too, you have to simply switch the primed and unprimed coordinates and replace u by minus u. So this gives us, we should write inverse Lorentz transformation. X is gamma times x prime plus ut, y is y prime, z is z prime, t is gamma t prime plus ux by c squared. This is these equations we call 5, right? So 5. X is, let me encircle these equations. X is gamma times x prime plus ut, y is y prime, z is z prime, t is gamma times t prime plus ux by, this is to be ux prime here. So t is gamma times t prime plus ux prime over c square. So these are our inverse Lorentz transformation. So they will permit us to find space and time coordinates in S if we know those in S prime. Right? So let us summarize our equations. So first we have Lorenz transformation. Then we have inverse transformation. Let me list them. If we write x prime is equal to gamma times x minus ut, y prime is y, z prime is z, and t prime is gamma times 1 minus, sorry, it's t minus ux by c square. Check them. X prime is gamma times x minus ut, y prime is y, z prime is z, t prime is gamma minus uxy c square. Now inverse transformations will be x is gamma x prime minus ut prime, sorry, plus, to replace u by minus u. So it's gamma times x prime plus ut prime, y is y prime, z is z prime, and t is gamma t prime plus ux prime by c square. Check them. X is gamma times x prime plus ut prime, y is y prime, z is z prime, t is gamma times t prime plus ux prime by c square. We've already written them. Here it is t prime also. X is gamma times x prime plus ut, t prime, y is y prime, z is z prime, t is gamma times t prime plus ux prime by c square. Let me check my Lorentz equations here. They're okay. There is we write also the corresponding interval transformations. Let me write first. Now, why we write interval transformation? Because they are useful when we wish to transform not a coordinate but a space or time interval, such as delta x prime equal to x2 prime minus x1 prime, that is the distance between two events as measured by s prime, or delta t prime, which will be equal to t2 prime minus t1 prime, that is the time between two events as measured by s prime, right? So let us write them, summarize them. So interval transformation. It means another color. This one. Delta x prime is equal to gamma delta x minus u delta t. Delta y prime is equal to delta y. Delta z prime is equal to delta z. Delta t prime is equal to gamma times delta t minus u delta x by c square. Let me check them. Delta x prime is gamma times delta x minus u delta t. Delta y prime is delta y. Delta z prime is delta z. Delta t prime is gamma times delta t minus u delta x by c square. And we have interval transformations for inverse Lorentz transformation also. So we write them. Inverse interval transformation. Delta x is equal to gamma delta x prime plus u delta t prime. Delta y is delta y prime. Delta z is delta z prime. Delta t is gamma times delta t prime plus u delta x prime over c square. Let me check them. Delta x is gamma times delta x prime plus u delta t prime. Delta y is delta y prime. Delta z is delta z prime. Delta t is gamma times delta t prime plus u delta x prime over c square. And remember, all these equations can be applied only in the case of relative motion in the x prime direction. And remember the definition of Lorentz vector gamma, which is 1 over square root of 1 minus u square by c square. Now I will give you some homework. Let me use this question first. This question says, particle moves along the x prime axis of frame s prime with a speed of 0.413 c. Frame s prime moves with a speed of 0.587 c with respect to frame S. What is the measured speed of the particle in frame S. Repeat the question. A particle moves along the x prime axis of frame S prime with a speed of 0.413 c. Frame S prime moves with a speed of 0.587 c. With respect to frame S, what is the measured speed of the particle in frame S? Question second. Find the speed parameter of a particle that takes 2 years longer than light to travel a distance of 6 light years. I repeat, find the speed parameter of a particle that takes 2 years longer than light to travel a distance of 6 light years. Remember, light year is a unit of distance, and it is the distance traveled by light in 1 year by definition. Another question. Question 3. This question says, what must be the value of the speed parameter beta if the Lorentz factor gamma is to be part A 1.01, part B 10.0, part C 100, part D 1000. I repeat, what must be the value of the speed parameter beta if the Lorentz factor gamma is to be 1.01, then part B says 10, part C 100, part D 1000. That's all for today. Don't waste your time. Go through all the video lectures, and don't forget to subscribe my channel. Thank you. God bless you. Assalamu alaikum.